Welcome back to Lecture 5 in our astronomy series. This is the fifth week, and we're going to be doing the chapters 9 and 10 devoted to Jupiter, Saturn, and the associated moons of these planets. So Jupiter is visible from the Earth. You can see it quite well sometimes in the sky, and even without a telescope. And Galileo, of course, was able to observe when he looked through his scope in 1609. He was able to observe not only the planet itself, but 4 of the moons, the largest 4 moons: Io, Europa, Ganymede, and Callisto. So we know from visual observation, just looking through earthbound telescopes, and you don't even need a telescope that powerful to be able to see this, but you can see on the surface of Jupiter, you'll see a series of light and dark colored bands, and then one very, very large reddish area, round reddish area, which is designated the Great Red Spot. Jupiter has a mass of 1.9 times 10 to the 27th kilograms. That's 318 Earth masses. The volume is 1,400 Earth masses. We could fit, actually, in terms of the volume of Jupiter, you could fit 1,000 Jupiters into the Sun, but you'd actually be able to fit 1,400 Earths into Jupiter. The radius of the planet is 71,500 kilometers. That's 11.2 times the Earth. Its density is 1,300 kilograms per cubic meter, and this suggests that it's obviously not made out of a rocky terrestrial type of material, but it's mostly hydrogen and helium, which are highly compressed. Since hydrogen and helium have densities at one atmosphere of only 0.08 kilograms per cubic meter for hydrogen and 0.16 kilograms per cubic meter for helium, then this would indicate, of course, that the pressure on Jupiter must be enormous. Jupiter's atmosphere moves by differential rotation, which is not possible. You can't possibly have differential rotation in a solid object. It's only going to work for a fluid. So the atmosphere itself, although it's very, very dense, actually moves differently, say, at the equator than it does at higher or lower latitudes. So, for instance, at the equator, the rotation is 9 hours and 50 minutes versus 9 hours and 55 minutes if we move north or south of that position. So we get a 5-minute differential rotation there. It's got a very strong magnetic field, and the magnetic field itself has a periodicity of 9 hours and 55 minutes. So that's not unusual. That's the average rotation everywhere except at the equator. The rapid rotation causes an equatorial flattening. This is something that you'd kind of expect just based on Newton's laws. So if something is moving around, if you've got an object that's moving around in this direction, it's going to flatten, sort of pancake out, so that the if this is starts out as a sphere and it's a gaseous or a liquid object, it's going to flatten this way, and it's going to actually increase in this dimension. So we see that in Jupiter. Calculations, however, would indicate that for an object of this size and speed, it should be flattened even more than it is. So if it had a uniform composition, that would be the case. But we know that the core, we know from this that it has to be composed of a core that's made of more dense materials than the rest of the planet. So it's probably rocky and terrestrial, kind of like the inner planets. And the core is going to still be very large. Still be a lot bigger than the Earth's. The composition of Jupiter's atmosphere is 86.1% hydrogen, 13.8% helium, and that leaves us approximately 0.1% is other gases And some of these gases are things like methane, ammonia, and you also have some water vapor. Okay, so this is the composition of the atmosphere. So I said that if you look at the surface of the planet, you've got these alternating dark bands, and then you've got light bands, and then dark bands again. One of these dark banded areas, you've got this large red spot that's in there. So what are these features? Well, from what we're able to gather, the lighter bands, which are called zones, and these are high pressure regions. So Jupiter kind of has weather patterns, just like you would expect, where you've got pressure differentials. You're going to have winds. Of course, the winds on Jupiter are much stronger than anything that you would see on the face of the Earth. So we've got these light and dark bands. The light bands are the zones. We also have other bands that are called belts, which are the dark bands, and these are low pressure regions. And you've got, when you have this alternating high and low pressure, what happens is that in the areas of low pressure, the atmosphere, the gases are actually going to move downward, and in the areas of higher pressure, they're going to move in the opposite direction. So the warm material rises to the surface in the low pressure regions. I may have said that in the opposite sense before, but it's the low pressure regions. Your material is going to actually rise, and in the high pressure regions, it's going to sink into the planet. So that is actually going to cause from the high pressure, where it's moving downward into the board, and the low pressure where it's moving upward out of the board. That's going to cause a flow that's going to go like that, and you're going to have this underneath this. You're going to have a zonal flow, where you're going to have enormous wind velocities that are going to be in some areas, certainly near the equator. You can get velocities as high as 400 kilometers per hour, but they're probably around 300 kilometers per hour on the average anyway. So this, causes a tremendous disruption or disturbances in the atmosphere. Okay, so under the bands, if we go under the bands, that's where we have the zonal flow. And as I said, it's a relatively constant movement of the atmosphere, of the air that's present in the atmosphere. But it's, again, unlike anything that we would have on the Earth. I mean, these would be winds exceeding 250 miles an hour. So we're talking about really enormous kinds of weather patterns. Jupiter's got a number of cloud layers. The stratosphere stretches to is about 50 kilometers wide, and the pressure is about 0.01 atmospheres. So this goes from 50 kilometers, let's say, down into Jupiter to 0 kilometers. It's not, when we say 0 kilometers, we're not really talking about the surface of Jupiter, because it doesn't really have a solid surface. But this 0 kilometer layer is just conveniently chosen as the top of the haze layer. So there's a layer of haze that's probably about 20 kilometers thick. And at this point, the pressure is about 0.1 atmospheres. Then below that 20 kilometer layer, a tropospheric layer, there's a kind of a white cloudish layer, which is actually composed of ammonia ice. So it's frozen ammonia, and this extends maybe another 25 kilometers or more. And at this point, the pressure is about 1 Earth atmosphere. So if we go further into the atmosphere of this planet, from about minus 55 kilometers roughly to about minus 70 kilometers, that's above that 0 point that I mentioned, below that 0 point that I mentioned before. We've got clouds that are composed of ammonium hydrogen sulfide, ammonium bisulfide, NH4HS, and this particular layer has kind of an orangish hue to it. It's not really understood exactly what's causing that, There was some speculation that there might be sulfur, there might be elemental sulfur in there, which would have a yellowish color. There might be phosphorus in there, is another possibility. These things would actually contribute this orangish color to this particular layer. We do know, however, that other things that are present in the atmosphere are ethane, which is C2H6, and an actual phosphorus compound, which can be synthesized on Earth, called phosphine. It's the phosphorus analog of ammonia. So instead of ammonia, which is NH3, if we replace that with phosphorus, we get PH3. So neither of these gases, though, has any color, so that really wouldn't contribute to the color at all. If we go below this level, from about minus 70 kilometers down to about minus 100 kilometers, there's kind of a bluish layer, which really isn't visible from the surface, but this is actually composed of water. And here the pressure is about 3.5 atmospheres. And below this, there's gaseous hydrogen, helium, methane, ammonia, and water. And this goes down to from about minus 100 to maybe a minus 150 kilometers. In addition to the great red spot, there's also some smaller white ovals, and there's also a brown spot that's in there. The smaller ovals are also storms. The great spot is a storm, is an enormous cyclonic storm that's moving in a counterclockwise direction. These brown ovals that I mentioned are breaks in the upper cloud layers. And in 2008, a baby red spot was observed that actually moved into the large red spot. It was kind of swallowed up by it and destroyed or absorbed. In March of 1993, a really interesting event occurred. The comet Schumacher-Levy 9 was discovered in March of 93. That's not when the event occurred. That was the discovery of the comet. Comet passes relatively close to Jupiter, and on its, I guess, next to the last pass before this event actually took place, it probably got a little bit too close to Jupiter and was torn apart. And the fragments the cometary fragments actually continued to orbit not just Jupiter. It was actually orbiting the Sun, but it continued to pass by Jupiter. On the next pass, which occurred between July 16th and July 22nd in 1994, these cometary fragments actually smashed into Jupiter's atmosphere at about 60 kilometers per second. And each impact created a brilliant fireball, which was easily observed using terrestrial-based telescopes. So these fireballs were hundreds of kilometers across with temperatures of thousands of Kelvin. The largest fireball was actually bigger than the Earth and had explosive forces that would be equivalent to like 1 billion nuclear weapons being detonated on the Earth. And one fragment that was designated as fragment G probably had an explosive force equivalent to the asteroid that slammed into the Earth's atmosphere some 65 million years ago during what is called the Cretaceous Tertiary boundary. This was the time when there was a tremendous mass extinction in which 90% of all the life on Earth was actually destroyed. And that fragment G was about equivalent in force to this fragment that actually destroyed the dinosaurs and most of the other creatures that were living on the Earth at the time. Oh, one other thing that I wanted to mention has to do with the fact that Jupiter is relatively hot based on what we would expect if what we were seeing, if the heat that we're seeing from Jupiter is just the heat that is reflected from the Sun. So we would anticipate that Jupiter's cloud tops, just based on solar heating, should have a temperature of 105 Kelvin. In actuality, the cloud tops have a temperature of 125 Kelvin. Now that may not sound like a lot. It's 20 degrees. It's only 20 degrees warmer than what's actually calculated. But based on Stefan's law that we saw in earlier chapters, we know that the amount of energy that should actually be emanating from this would be equal to sigma times T in Kelvin, the temperature in Kelvin, to the fourth power. So this is actually the flux, the energy flux, F. So if we actually take these two values and we plug them into the equation, what we'll find is that this fraction, which is, since we're actually comparing the flux for two different t's to the fourth, the sigmas are going to cancel out. So it's just going to be 1 t to the fourth over the other t to the fourth. So we have the values 125 and 105. So if we take 125 and divide it by 105, if we raise these values, this is the ratio of these two things. If we raise that fraction to the fourth power, it's something greater than 1, but when we raise it to the fourth power, we're going to get something like 2.01 approximately as the value. So it's actually telling us that the energy flux is twice, will actually be twice what we would have anticipated based on, if in fact the temperature were only 105 Kelvin. So that 20 degrees of extra heating actually gives us an output, a temperature output that's twice as great as we would anticipate. Jupiter actually emits from this, because of this, 4 times 10 to the 17th watts more energy than it receives from the sun. And the source of all of this is believed to be due to a slow release of actual gravitational energy from the time of the planet's formation. So the tremendous gravitational energy is actually being dissipated in the form of heat. Jupiter's surface below minus 100 kilometers, the temperature is about 300 Kelvin. So actually at that particular point, although the pressure is enormous, it's still, well, not enormous, but still very, very great, about 10 atmospheres. But the temperature of 300 Kelvin is actually comparable to an Earth's temperature. So it's been postulated at various points in time that if some form of life could actually exist in Jupiter, on Jupiter, well, let's say in Jupiter's atmosphere, it would probably be somewhere in the zone where it's warm enough, although the pressure is very, very high. Nevertheless, there would be a possibility if life could somehow form that's where it would you'd actually find it, in that zone. But this is really unlikely, because in that zone we now know that that's a layer of mostly of hydrogen to a depth of about 20,000 kilometers. Below that zone, that's where you start to get the very, very dense hydrogen atmosphere, and that builds up all the way down to the point where you get a transition where the temperature is actually about 11,000 Kelvin and the pressure is around 3 million atmospheres. So at that particular point where you've got this very, very great pressure and temperature, something very interesting starts to happen to the hydrogen. So if you remember, those of you that have already taken chemistry and those that are about to take it possibly this year, what you will learn is, when you study the periodic table, is that there are a group of elements which are designated as group 1 that fall on the left side of the periodic table. And these consist of elements that have very, very similar kinds of chemical properties, and in some cases physical properties as well, with one exception. So there are a series of metals. So you have group 1, and they're lithium and sodium and potassium. These symbols come from these strange symbols come from the Latin names for these elements. Natrium, this is sodium, and kalium, this is potassium. And then you've got rubidium and cesium, and a radioactive element called francium, which is a very, very rare element. But all these things are metals, and they're relatively low melting metals. Right above lithium, however, is another element, which is hydrogen, the most abundant element, the most abundant substance in the universe. But hydrogen, unlike the other ones, is not a metal. Until you get up to pressures in the 10 to the 6 atmosphere range, then hydrogen actually becomes metallic, which is very interesting. Now, we know this because we've actually made metallic hydrogen at pressures of 1 million or more atmospheres. And the way you can do that is, and you can actually observe it, and metallic hydrogen, believe it or not, actually, if you look at light coming into it, you know, what reflects off of it, these elements are all kind of silvery. I think when you get out to maybe cesium, there's a slight shift in the wavelength, and it might have a slightly different appearance to it. I don't think I've ever actually seen, yeah, I have seen metallic cesium, but I can't remember, but it's not as silvery as the other elements. Hydrogen, however, has a kind of a golden color to it when it becomes a metal. Of course, it's a colorless gas at 1 atmosphere, but at 10 to the 6, and one of the ways you can do that is you can take an anvil, you can actually have 2 anvils, and you can push these things together. And if the anvil is made out of diamond, which is transparent, you can achieve these very, very high pressures, because whatever pressure you're getting here, where it's kind of wide, the pressure is greatly intensified when this comes to a point. So you have these relatively pointy diamond anvils, 2 of them pressing against one another, and when that happens, you get tremendous pressures at this point. It's possible to actually look through here and see what you've got, and that's where they've observed the formation of hydrogen metal. That's not in your book, but it is a fact. Okay, so we've got metallic hydrogen in there, and that actually accounts for the fact that there is a very, very large magnetic field that is being produced by Jupiter. I mean, Jupiter has, of course, has this core, and there could perhaps be some iron in the core, but the amount of iron that would be present in Jupiter's core, it being more like a terrestrial planet, the core, does not account for the really enormous magnetic field of the planet. What does account for it, though, is the dynamo effect. Remember, we have a dynamo when we have a molten metal that's actually, or a fluid metal, let's say, in this case. I don't know, probably don't want to talk about this being molten hydrogen. It's not liquid hydrogen, but it is hydrogen that is metallicized because of the very, very great pressure. And that is now moving, it's in motion because of the planet's rotation, and that is producing a dynamo and making a pretty large magnetic field.